I'm going to be demonstrating and exploring some properties of a 3000 farad capacitor for my course in Design of Electromechanical Systems at NC State University. This supercapacitor, purchased from eBay for $40, has excellent power density. It puts out 2.7 volts, 1900 amps maximum, which gives you an amazing 5 kilowatts of power, or 7 horsepower, in just a little over a pound in a very small volume. This battery is a latest technology lithium iron phosphate battery, and it can be charged at a rate of 14 amps, which is very good. Now, as you can see here, comparing the lithium iron battery to the supercapacitor, the lithium iron battery with its 210 cranking amps gives you a 605 kilojoules, which is a whopping 9 times more than the capacitor. Next, let's consider how much the technology would need to improve for capacitors to have the equivalent energy of this lithium iron battery. So what capacitance would be needed? Well, if we look at the battery and compute an equivalent capacitance, we come up with 8.4 kilofarads. With 2.7 volts, we need 6 of them, and we back out the capacitance of each one, it would take 50,000 farads required. And so clearly, the technology needs to improve another magnitude or so. Just for kicks, I wanted to try out charging the capacitor with a AA battery. This battery isn't that fresh. I tried a fresh battery earlier, and it had a peak current of 5 amps, but quickly dropped to about 3 amps. Okay, now we're ready to charge the capacitor. So the ESR on the capacitor is only 0.47 milliohms, so it would draw a lot of current if it could. Okay, now it's been charging for 10 minutes or so, and the power supply says it's reached its 2.6 voltage limit, and now the current is dropping. And this matches the calculation pretty well. For 10 amps, 3000 farads, 2.7 volts across the capacitor, it should give me a 3.3 millivolt per second charge rate, and to give a total time of 13 minutes. Okay, now let's do a quick check just to see that the capacitor has the horsepower we think it does. It looks good. Yep. Another supercap application that interests me is in the low current end of the spectrum. This is where the quick charge property of the capacitor would be very beneficial. So you could have this backup flashlight that you can charge the capacitor, and it holds a good charge, and so then you can have your hands free for an hour to work on whatever you need to work on. So using the LED, this is an example of a 3-watt LED. It's a high power, high intensity LED that I've soldered to a heatsink. So we should be able to hook this up directly to the capacitor. It's a little low on voltage, at only 2.7, so hopefully it's not below the threshold. But in an actual design for the flashlight, you would work out something with a closer match on voltage. The calculated time that the LED could be lit is the energy divided by the power, or 1 hour. So let's give it a try and see how it lights up. And it does light up. Now, it's not as bright as if you had the correct 3.2 volts. And here it is with a 3.2 volt battery pack. 2 AA batteries. Major difference. So you definitely want to have the correct voltage.